All right, let's start off with this one. I want to look at what happens when I have a magnet, a bar magnet with a magnetic moment M, coming close to a wire carrying a current. This guy's got a current of 1 ampere, and M is equal to 10 ampere meters squared. So now this guy's got a field, right, coming out of him, sort of like that. It's already getting messy. And this guy is therefore going to react to it because he's got a current passing through. So how are we going to deal with this? That looks hard. Can we turn this into an easier problem? Well, we could if we used Newton's third law. So Newton's third law, you remember, says that the force on the wire is equal to the negative of the force on the magnet. So instead we might look at this wire as producing a field, which it does, right? So if we've got 1 amp going to the right, then we have a field coming around this way, like that. And we have our bar magnet here. And so we'll have another loop coming out that way. Now this field we know drops off as 1 over r. It's fairly benign. So since we know how that field works, what we can do instead is to calculate the field on the bar magnet. Now the bar magnet, we could either try to look at what happens at every single point, or we can use the approximation we were using previously, where we say the bar magnet is more or less a dipole with these fake magnetic charges on either end, which means then we only have to calculate the field at 2 spots. The field here, where the plus is, so let's call that B plus. Where the negative field is, we have a minus QM, or B minus. It's going in the opposite, or the field is going in that direction, so that's B minus. That's the force this way. All right, but the force is going to go in the opposite direction here, so there's going to be a net force this way because the field closer to the wire is stronger, and there's also going to be a torque, but we're not going to worry about the torque here. We just want to figure out the force on the wire. So we know that the net force on the magnet is going to be going sort of into the screen, so kind of coming out of the screen over here is going to be the net force on the wire, which is going to be exactly equal to the force on the magnet. Now the only thing there is this force is going to be distributed over the entire wire, which basically we're assuming is infinitely long. So there'll be more of that force close. There'll be lots more of that force close this way. But there'll be a lesser force over here and then even lesser force there until it gets to very, very small at the edges. But there's going to be the force is going to reduce. Now we're not going to worry about that. We just want the total force. But there is a force there. This is actually going to cause the wire to deform if it can. All right. So that's the basic idea. So we find the field from the force on the wire, right? So that's this guy here. We'll find the force over here. It's going to be QM times B plus minus QM times B minus. Or just QM times the difference of those two fields. So let's see what we can do to find those two fields. Well, B plus is equal to mu naught, which is 4 pi times 10 to the minus 7 Tesla per amps per meter. And the I is 1 ampere. It's all divided by 2 pi times the distance from here to here, right? So that's going to be 15 centimeters minus 5 centimeters, 1/2 of the length of this, which is 10 centimeters. So that's 0.1 meters. Okay, so we've got, cancel these, so we have a 2 times 10 to the minus 7 times 10, so we have 2 times 10 to the minus 6, which means we have 2 times 10 to the minus 6 microtesla, or Tesla, which is equal to 2 microtesla. Okay, so that's B plus. Now B minus, we do exactly the same thing, only we put a 0.2 there. So it's actually going to be exactly half the distance, because we're going to look here at 20 centimeters, or it's twice the distance. That means twice the distance means it's going to have half the field. So B minus is just 1 microtesla. Okay, so that's good. We can use that. Now to put that in here is fine, but we need to know what QM is, and that's what we're going to do next, is we'll find the effective magnetic charge. Let's see, and we do that with our definition M equals QMD for the magnetic dipole. I sneezed and then the air conditioning came on. Strange. Okay, 10 times, usually it's the other order, right? Let's see, 10 amps per meter, excuse me, times QM times 1/10 of a meter, right? Because that's 10 centimeters is 1/10 of a meter. So that means QM is equal to 100 amp meters. That's good. Nice and simple. We're okay with that. Now we have to go into finding the force, which we said was QM B plus minus B minus. Alright, so that's going to be, okay, this is B plus, this is B minus. That's going to be 100 amp meters times 2 microtesla minus 1 microtesla, which is just 1 times 10 to the minus 6. So that's 100 times 1 times 10 to the minus 6. That's 1 times 10 to the minus 4 amps times meters times Tesla. That's going to be equal to 100 times 10 to the minus 6 newtons, micronewtons. Okay, so that should be sufficient. That gets us to where we're going. All right. So when you have something like this, you just have to keep working your way through it. We have to find the QM and the B's, both of those B's. And doing that is just applying the formula that applies to the correct situation. In this case, the situation is the situation for a wire, current passing through a long straight wire. It could have been another situation, but we don't have that many situations actually to work with. So we go back to use our dipole approximation, just like we did previously. This actually looks a little bit like, if you remember, the problem that we had with picking up little pieces of paper with electricity and with an electric dipole. And in that case, we just had a line charge, and then we had to polarize the little pieces of paper, and then they wanted to float up to the rod. So it's the same sort of thing, only now, because it's magnetism, the forces are in a sort of orthogonal in perpendicular directions. That's what we see in this. All right? Bye now.